Okay.
It's fine, thank you. Well, thank you for the generous introduction. Uh, I I'm not the perfect person to speak to Mariam, but I will try to answer any queries. So first, before we start, hi everybody. I'm Nikolai. I will be monitoring Slack on my screen, and I will try to be presenting the tutorial. The tutorial is going to go. Um, we're following the blog post step by step. We are going to start by getting set up. So what I want people to get from this tutorial is to try out efficient machine translation on their own machines. And after we try it out and see what we can get, we're going to move to actually seeing how to create those efficient systems. The tutorial is going to be recorded and made public. The video is going to be made public later, and the blog post is going to stay on, so you can go back and refer to it. You can send me emails, you can leave comments, anything, any other questions, I'm always ready to answer. Okay, so let's get started. So the first thing that I want everybody to do is to install Sacriblo on your systems. If you're running on the server, I think it's already installed. Let me double check. Uh, but yeah, I'm sure like I've left instructions how to do it. Let's see, Sacriblo is already installed. Then for those that are not using the cloud instance, it's done through pip. The next step is to get Marian installed. I have written compilation instructions here in this small code selection. You can just copy them to your machines. If you're not using the cloud instructions, if you are using the cloud, Marian is already installed, so what I want you to do is to just create a Marian dev directory and then create a build directory. This is just to simulate the environment that you would have if you download and compile Marian yourself. And then create a symlink. Compiling Marian takes a while, and it's also dependent on having a BLAS vendor installed. We prefer to have Intel MKL, and I have left instructions on how to install MKL on Ubuntu, and there's a couple of other details here about how to compile Marian on Mac. It should also be able to compile on Windows, though installing MKL is a bit works a bit different there. Next is getting the data. If the data is already on the server, if you're running on the cloud account, so just copy it from opt and extract it in your home directory. This is this needs to be done in your home directory, so you should not Marian dev, the Marian dev directory should not be inside the empty marathon, and vice versa. So you want to have a directory structure where I'm just gonna share my I'm just gonna show you my terminal actually. So basically this is my cloud account here. I'm extracting. It's gonna take a second or two. Okay, technical difficulties. I'll fix this in a second. In the meantime, I'm just gonna leave this tutorial because I'm sure it's gonna take a few seconds for everybody to get to the point, to this point. Okay, Graham is watching the tutorial and he installed 3, so thank you very much. So now that you have 3, your if you're on the server, your folder structure should look like this. You should have, in the parent directory, you should have Marian dev and empty marathon, and then you should have the various teacher and student modules. So normally when we do this tutorial in person, it's a bit easier to get some feedback of where people are. For some reason, when I'm sharing my screen, I can't see the Zoom chat. So I don't know if there's any questions there. I see there is a hand raised for Manuel. Or is this just a... Okay. I am going to assume that we have Marian installed at some point and we have the data downloaded. And please, anybody, if you have questions, just ask me. Can I not see the chat? Just chat. Okay. Okay. Good. So the next step. So what we're going to do is we're going to start with the teacher model. When we are doing efficient machine translation, the step that we do is we train a big teacher model. This is your transformer base or transformer big configurations if you're familiar from other papers, and then we use that teacher model to train the student models. I'm going to talk about training the models later in this tutorial. For now, we're just going to look at the configuration options of a teacher model and try to understand why it's going to be slow to decode. So if I go and maximize my screen, I'm gonna go cd empty marathon es.teacher.big, and then I'm going to cut config.yaml. And this is my configuration for doing a translation of English to Spanish teacher transformer big model. This is an ensemble model of 2 separate transformer. Was it transformer base or transformer big? Of 2 separate transformer big models. They have the same vocabulary. We do beam search with size 4, and we do length normalization. Oh, okay, font size too small. Okay, I'll do the same for the browser when we switch to the browser. So this is the basic configuration. So I'm gonna go back to the browser. I don't want you to be running this translation. Okay, let's see. Yeah, I hope this will be a bit easier to see. Maybe you can do a bit more. Yeah, okay, that should be fine now. So this is the translation script that we have. It's basic.translation.sh. It sets the Mariam path. This is why I asked everybody to create a symlink. It says the source target language, sets up Sacriblo with the to create a test set, which is the WMT13, and then translates. It calls Mariam Decoder, does the translation, and then it evaluates. Now, I don't want people to be running the system because it is really slow. How slow exactly? Well, I run it on a relatively large system with 16 threads, and I got total time of 4,597 seconds to translate 3,000 sentences, which is more than a second on a sentence. Now, this is really too slow, and the reason why this is too slow is not because the model is big, but because not only because the model is big, but because we are not adjusting the mini batch size. The problem with this baseline system is that we're only translating one sentence at a time, and when you're translating one sentence at a time, your device gets tall and skinny matrices, which are not efficient, not as efficient to multiply on this hardware. Whereas when you create a mini batch, we make our matrices more so approaching a square, which will make translation faster. Now, in order to do this, we change our configuration file a bit. We add the following options: mini batch 16, maxi batch 100, maxi batch sort, and workspace. This basically means that when we are looking through the file, we are going to read 100 sentences at a time, sort them by length, and then group them in groups of 16 based on length similarity, and then send them for translation as one mini batch. And workspace 4000 means that for each worker, we are going to have 4 gigabytes of memory allowance for it to use to store its activations. One thing that I forgot to say is that when translating, when you run the script, you do basic translation CPU threads n, and as n, you want to put in the number of your actual CPU threads as opposed to the number of hyperthreads. So if you have one of those Intel or AMD processor that have more than one thread per core, use just one thread per core, because having extra threads doesn't help for translation speed. And now that we have done this, we have increased the mini batch size to 16, and now on the same hardware we have translation time of 652 seconds. If we compare back here, this is about 8 times, 7 times performance improvement compared to the previous system just by specifying the mini batch size, and we get exactly the same blue score. So there is no reason not to do this, unless of course you're out of memory, because if you the bigger the mini batch size requires more memory. Yes, somebody is trying to get the data. Use the mirror from nbugoychev.com. So let's go back a bit. Just do this. Right. So this is pretty much as we can do with the teacher model. Then we're now going to start running things ourselves, which I hope is exciting. So now we're going to run on the student models. The student models are what typically machine translation providers use to run in production. The student models are trained on the output of the teacher model, or models in the case of assembling, and they are trained to overfit on the distribution of the teacher. Basically, I have linked later on, we're going to talk about it, and I have linked various papers that explain it. But the thing is, natural language is really complicated, and for the student models, they have less than 10 times the parameters of a teacher model. They're not as expressive, so they can't learn, or at least maybe they can, because there is a question about search error versus model capacity. But it is much more difficult for the small neural networks that we use with the student to fit to the natural language. However, they're quite good at fitting teacher distributions. So instead what we have is we have the teacher translate its training set and then train the student model on that. And this gives us several advantages. So first, beam search is unnecessary because we get the same quality regardless of the beam search size. The distribution at the output layer is very peaked, which is why beam search doesn't change the translation. We also don't need ensembling. The model is tiny, and yeah, we're going to talk about constructing it later. However, the student model, of course, has slightly lower quality. The other thing that we need to note is that because we're not doing beam search, we don't need to do the softmax at the end. We can instead take argmax. So the way we do this in our combination, we go to student. I'm just gonna go back to my terminal. So let's see, enes.student, and then we do cat config.yaml. So if you're following the tutorial, you should be in this directory. I'm gonna go back to the browser. So the main differences between the teacher model and the student that we have. First, we do this bit here. We set the max length factor so that the target sentence is never longer than 2 times the source sentence. And the next thing that's important to note is that we skip the cost. This is the option that says do not do softmax at the final layer, but take argmax. Also, you should notice that we're using just one model here as opposed to an ensemble. And to run the baseline, you can do okay, I'm gonna open another terminal and I'm going to run it on my machine, as everybody should be able to run it on their own machine. So basically you do basic translation.sh, and then you do CPU threads, and based on how many threads your system can support. So I'm just gonna do this here. Let's increase the font size, and I'm going to do this is on my own machine. Basic translation.sh CPU threads 12. And now we are translating with 12 threads. It's gonna take maybe about 2 minutes to translate. I'm just gonna move down a bit, and we're missing the same optimization that we did last time. What does normalize of 10 mean? So normalize is the length normalization, because longer sentences will naturally have lower score. So you normalize based on sentence length. This is a default option, I believe, with the decoder, but I'm not sure. So yeah, while this is translating, it's still not that fast. It's off by default. Okay, thank you, Graham, for the tech support. So to be honest, length normalization is a hyperparameter that you need to explore. Depending on the language pair and the system trained, you might get much better results with the length normalizations of 2 or 3 or 0.6. It's yet another hyperparameter that needs to be searched. So yeah, going down, the next optimization that we're going to do is I'm just gonna get this to be a bit smaller again. The next optimization that we're going to do, okay, it's actually ready now. We translated, it took us 120 seconds, and we got a blue score of 35.2, and you should be able to do that on your own at your machines. Let me double check how is the cloud doing. Okay, not too many people are actually running it, so you can go crazy. You can specify 62, 64 threads probably, if you're the only person using the cloud. So okay, I'm gonna minimize this again. Oops. So the next optimization that we're gonna do is we're gonna change the mini batch size. It's exactly the same config as the other one, except this time it's the same configuration as with the teacher model, and I'm just gonna do it here. I am going to do basic. I'm going to do batch translation, and I'm going to put CPU threads 12, and let's see, am I gonna run out of RAM? I might, and I might not run out of RAM. I haven't tried it. And okay, I didn't run out of RAM. And see, that took just 15 seconds. This is down from 120. So like we nearly get 10 times performance improvement by applying batching. This is very important to do because it's the easiest optimization that you can do. It always improves performance and doesn't decrease translation quality. And unfortunately, it is off by default. The next thing that we're gonna move now, this is lexical shortlisting. The way lexical shortlisting works is basically when you're translating, the way to think about this, you're using a dictionary. You see the source sentence and you want to produce the target sentence. Instead of producing and instead of like checking against all vocabulary items for each word of the target sentence, what you want to do instead is to go through the words and look at a dictionary and find the likely translation of each word. And then you limit your vocabulary only to those likely translations. This in practice with mini batch, with our mini batch size, this will does using shortlist without batch. So no. Okay, yes and no. You shouldn't do lexical shortlisting without batching, and you shouldn't do lexical shortlisting on the GPU. We are going to talk about this later, but recently we were made aware that lexical shortlisting, when the mini batch size is small, lexical shortlisting results in much poorer translation quality than expected. And the reason for that is mostly that we are getting not enough. Basically, the shortlists are kind of bad at capturing idiom expressions and bad at making up, figuring out subword vocabulary. So when you use a shortlist on mini batch 1, you can get a severe drop in blue. Okay, I'm just gonna show it quickly here. So let's see, cp config.yaml.shortlist, and then I'm going to add the shortlisting bits to the here. Let's see. This is the shortlisting bits. The shortlist, yeah, and I'm just gonna add them here. And I am going to here, and I'm okay, so let's see, basic.shortlist translation CPU threads 32. So you're now going to see, yeah, this is going to take about, no, 32 threads is a bit too much, I think, for this. Yeah, let's try 16 threads on my machine. So yeah, this is going to be faster, but it's also going to yield a lower blue score than 35.2. Okay, it didn't yield a lower blue score. Surprise, surprise. But we have done experiments in which it did deliver lower blue score, so I would caution first try it out yourself on your data. Make sure the quality is good before you start using it unbatched. I personally wouldn't use it unbatched. Okay, But now that we have seen that I'm wrong, let's proceed with the tutorial. Let's try the batched shortlist translation. Shortlisted translation.sh CPU threads 12. So it's I have added we are down to, so previously we were at what? We were at 15 seconds, and now we are down to 10 seconds. So we shaved off a third of our runtime by using a shortlist. So the script itself, the difference is that we generate a binary shortlist. This is our shortlist, lex.s2t.gz, and we say to the shortlist, always take the top 100 words, and then always take the top 100 words from the vocabulary, and the top 100 translations of the words according to our dictionary. If you're having quality issues, like the ones, so this parameter, it used to be 50 in our previous work, but I have increased it to 100 precisely because we saw the drop of performance when running it unbatched. So yeah, if you're running it unbatched and you see a drop of performance, increasing the shortlist items will help. But again, even though the translation quality loss is not evident on blue, it might still be there. I have heard people complaining of getting more literal translations with a shortlist compared to without using one. Right, next. Yeah, we talked about yes, Roman. Yeah. Why can? Yes, that's basically the two parameters that I have here. Let's go back. So the two parameters here, 100 and 100, this says top 100 words from the vocabulary and top 100 words according to the shortlist. So you can change this to like 1,000 or 1,500. Yes, basically, to answer Oleksi, yes, you can just include the top n words, and we already do that. But this is still a noisy process because, especially with idioms, the translation model might have learned the idiom very well, but the shortlist would be absolutely unable to capture the words if the idioms between the two languages, like for example in Bulgarian, like the popular English idiom "it's raining cats and dogs" in Bulgarian would be translated as "it's raining mops," you know, like the thing that you use to wipe the floor. It's or like it's more like it's pouring out of a ladle. So there is no way for the shortlist to get that, because the words do not have the literal translation of the words would not be captured by it. Yeah. Okay. The next step of this tutorial, we are going to talk about quantization. So in normally our models are trained in FP32, which is floats, and they're decoded also in floats. However, it has been shown that we don't necessarily need a 32-bit number to efficiently decode a neural network. We can efficiently decode we can reduce the accuracy of each number to a lower precision, such as 8-bit integers, and we shouldn't really lose much quality. However, we massively improve the speed. So in our example, we are going to create a int-gem 8 model. We're going to talk about the different backends later on in the tutorial. And then we're going to run batched shortlisted translation. In this translation, we are going the model is first let's see, batch.shortlisted 8-bit translation.sh, and then we do CPU threads 12. So all of this that you're seeing is output of Marian convert, showing that the model is getting converted, and we see we shaved off about a second of the translation, and we got 35 blue. So the thing is, we shave a lot more than a second of the translation, but we have a very small test set. So if I do, let's say, if I do a CPU threads 1, you're going to see the time for one thread as opposed to and then we're going to check the batch translation with one thread, and you're going to see much more accurate numbers, because at the moment our test set is 3,000 sentences. You can't really see speed difference with 3,000 sentences. So if we have the batch shortlist translation with one, so one thread here is 24 seconds, and we're gonna see this one, it's gonna be probably about 35-40 seconds. Reducing so quantizing the model to 8 bits, of course, will result in in a bit of a decrease of translation quality. Yeah, so here you see yes, we shouldn't be using shortlist with the GPU. I will talk about this in later in the tutorial when GPU decoding. So we had previously 24 seconds and we have 30 now. So Going to 8-bit integers, we gain about 20% of performance. We have a different branch, which is focused on speed, where our quantization code path is much faster than this. I'm gonna link it later, and I'm going to link tutorial about how to use it if you need that speed. But for most people, this is just a tutorial to see what you can expect. So now let's see the results summary. This is on a system with 16 threads and 3000 sentences, and we have the basic teacher got 36.5 blue and took more than an hour, and we went all the way down to 7 seconds at a cost of 0.5 blue. Going down from a teacher to the student model, we lose 0.2 blue, and then we lose another we lose 0.3 blue, and then we lose another 0.2 blue at quantization. Now there are methods to decrease the blue score lost at quantization. I'm going to speak about it later in the tutorial, but it is important to see this difference. Now, for the student models, the numbers are very close because our test set is very small, so instead I did decoding with one thread, and you can see the performance gain. It's important to use the system that does the job for you. Depending on how much speed you need, how much translation you have to do, maybe like you want this 0.2, you don't want to do quantization, maybe you really want it, like the 6 seconds here, they do add up. In our faster branch, we have about 30% on top of that. Maybe this time would, in our branch, I would expect this time to be more like 14 seconds for the 8-bit students. So it really depends on your quality trade-off. Okay, so this is the interactive part of the tutorial. I hope I got everybody's attention. I hope that you're interested in what I had to say. Now we're going to move to how exactly to train our own efficient models. So this year, I hope somebody can help me from either Roman or Graham. If you recall the results of human evaluation, yes, for this year we did human evaluation for teacher and student at the W efficient machine translation. Yes. Yeah. That's it. We have number of student configurations. I have actually shown you the tiny one, but there is also a basic one, which is slightly bigger and slightly slower. Yeah, I'm gonna talk about this later. I'm also going to, after the tutorial is done, I'm keeping notes at the moment so that I can update it with all the questions that come up during the talk, and you can go back to it later on. Okay, so now training. So first, training a student model starts with training a good teacher model. There is plenty of resources on the internet about how to train a good teacher model. I'm sure that most of you already know that because you work in companies that sell translation models, or you're doing your PhDs in translation model. But basically, a very high level view is the first thing that you do is you need to clean your data. Most people like to have their own cleaning scripts that specifically cater to the idiosyncrasies of the corpora, but the least that you can do is you can use the clean corpus and Perl. That's part of most scripts. Then the next thing that you want to do is you want to train a reverse model for back translation. The back translation system needs to be good quality, but not, it doesn't need to be excellent quality. So I have provided here a configuration file that you would want to use for training a back translation system. I have taken, I'm assuming input is German and output is English. The important part to take from this configuration is where did I put that? Did I forget it? Right, so there should be a model type here. Yes, task. So the thing that there's a lot of the task parameter here, it sets a lot of hyperparameters. I think I have a link somewhere to it. Yes, so if we go here, when you specify task, what happens actually inside Marian is it looks at it matches task and sets all the parameters. So that says encoder layer 6, decoder layer, dimensions of embeddings, tight embeddings, transformer heads, and this part here takes care of scheduling. So specifying the task alias here will transformer base, you will get a known working configuration. You don't need to, I mean, you can experiment, and I encourage people to experiment, but if you want to get something safe to start with, just use task transformer base. Then the other parts of this configuration file, what to validate, cross entropy, perplexity, blue scores, the deficit, and then when decoding you specify beam search, normalization, max and factor. Mini batch fit is related to the workspace parameter. Basically, it tells you you have a memory budget of 12 gigabytes, use as many sentences in parallel that fit in 12 gigabytes. This configuration should work for 16 gigabyte of GPU, but if you're running GPU with less memory, obviously decrease the workspace to say 8 gigabytes if you're running 12 gigabyte GPU, and you can also decrease the valid mini batch if further, like it needs to be a multiple of 8. This is how fast this parameter here determines how fast translation is done during training, the translation for validation only. And I mean, you can increase it further, but honestly you get the majority of the benefit with 8 already because the dev sets are very small. Now, once you have trained your reverse model, you want to take your monolingual data. I assume you always have some monolingual data. Say you're creating German to English model. You have just trained English to German, and you want to back translate your English data that comes from either newscrow or common crow, or maybe some in-domain dataset that you have. The crucial thing for the configuration here is that you want to turn on the option of output sampling. This option tells you to produce to use I think it was gumbo noise at the output layer to produce the translations, and this is shown to produce back translations that yield higher blue scores when training the full model. I have forgotten to add the exact paper reference, but I can do that after the tutorial if you're interested. Next, we proceed to train the actual teacher model. We want to use our genuine training data and our synthetic data. Now, how you should use it, some people prefer to upsample the genuine data so that it's the same as the back translated data. Most of the time you have more back translated data. Sometimes having a ratio of 3:1 synthetic to parallel data might not really matter. Some people prefer to add a tag to tag the back translated data. This is shown to work better in some performance. I will add this in the tutorial later. So for training the teacher, you have two options. Either to, well, you have many options, but the simplest thing in Marin, you can use data weight instead of upsampling. Yes, this is true. Thank you, Toms. So you could train your teacher. We have transformer base or transformer big configurations. If you have more than 5 million sentence pairs, you probably see gains from using transformer big. If you're using transformer big, you have 12 gigabyte GPU, adjust down the workspace to 10 gigabytes and provide the parameter optimizer delay too. The optimizer delay parameter is going to basically perform two backward passes of 2 mini batches and then sum the gradient before running an optimizer step. This way you simulate a bigger mini batch, and bigger mini batch are helpful to stabilize training. They also increase training speed, but in the case of transformer big, mostly we want to do it for the bigger mini batch, which leads to better training results. We have the task aliases as we showed earlier. Now the next thing is that training one teacher model is good, but training more teacher models is better. As you remember earlier in the tutorial, we had our teacher model was an ensemble of two models. The way ensembling works is basically you train the same model, but you provide different random seeds. So if you look at here, I have the seed parameter of 1, 1, 1, 1, 1. If you want to create ensemble, you create a new configuration, you change the location of the lock in the model, and you provide a seed of 2, 2, 2, 2, for example, 3, 3, 3, 3, and so on for however many models you want to use in ensembling. This is going to lead to, obviously, like every time you add another model, this massively increases training time, and it also massively increases decoding time because you're doubling the work of the decoder. Now, assuming that you have trained the teacher, which will take a while, we can move to training the student. The student model is trained to approximate the teacher distribution, and the easiest way we can do this is we can decode our whole training set, including the synthetic data, with the teacher model that we have just trained. Um, we're going to use our best quality configuration, which was, let's see, yeah, you probably want a quality of, yeah, you want a beam search size of 4, you want normalized inward penalty. This is what you want your configuration to look like when you're decoding the data for the student. You want, so it is possible to use quantization or shortlist for translating the student data in the teacher, although I would not recommend it because you're already losing a bit of translation quality and you're doing this work only once. You want to give your student the best chance to work from the highest quality of data. If you're doing the translation on recent NVIDIA GPUs, that's 20 series and newer, you can add the FP16 flag to your decoder. This quantizes float 32 to float 16, which actually doesn't really result in any different translation. This is already big enough precision, so you can do that and enjoy about 30% faster decoding on the GPU. We're going to talk about GPU decoding later in the tutorial. The next thing that we want to do is we want to produce the shortlist. Our student models are all trained with guided alignment, for which we also need to compute the word alignments. We do this by training IBM model with fast align. We have all the information about sorry, just double check. Okay, we have all the scripts about how to produce the alignment and the shortlist, thanks to Roman. They're on GitHub here. What you need to do is you need to clone this repository and you run install.sh, which is going to get all the necessary files, and then you set a path to Marian, path to the vocabulary, the corpus and the target, and then you run this script which is going to run fast align, produce the alignment model, and produce the shortlist. And that's it. Once we have generated the alignment model and the shortlist, which shouldn't take that long because it's fast align, depending on how much data you have, it might be a few hours up to a day at most. And then you can proceed to train the student. We have various different student configuration. The student model is trained on the original source text and the synthetic translated target text that you just produced right now. You give it this data set. So here I'm showing you the tiny configuration prefix that I have used. But we have multiple prefixes, again, courtesy of Roman. They're all on GitHub, so I'm gonna add a link later, but if you go to models, we have font size, we have student base and student tiny. I have given you the configuration of the tiny student. Base student will have slightly better translation quality, closer to the teacher, but it also translates slower. Now what you're gonna do and what you're gonna use depends on the language pair that you have, the systems that you have. It's a trade-off. Yeah, I have just copy-pasted those scripts. you do the full model training. One thing that you should know about training a student model is that you really want to overfit on the teacher. So you want to go through your training data multiple epochs, and here we have set early stopping 20, which means that we only stop training if cross entropy has not improved for 20 iterations. But it is quite often the case that a student model will appear to be stalled, and then after 10 validations it will improve cross entropy a bit. So you need to be patient. Another thing that you should be aware is that what was I talking about? Yes, you can also further translate data with your teacher. You can translate monolingual data with your teacher and add that to your student, even if it is data that the teacher has not seen during training. This will also increase the quality of the student and will likely make it easier for it to translate. The next step is quantization fine-tuning. So after you have trained your student model, and if you want to quantize it to 8 bits or 16 bits, you saw that the quality of the model decreases. So one thing that we can do to avoid this decrease in translation quality is to train for a bit with a damaged gem implementation. So yes, ratio used for back translation data. Usually back translation is more than the genuine data. I think that we have used up to 100 to 1 in terms of back translation to genuine data. In general, the more back translation you have, especially if it is in domain, the better your translation quality is going to be. But there is usually a limit of how much patience you have, how much computational resources to it. I think that using a 10 to 1 ratio of back translated to genuine data is completely fine. Using 3 to 1, it really depends on how much data you have. Okay, so quantization fine-tuning. Basically what we do here is we have a gem yes, Kenneth posted a link to a paper that I should add. So there is another question. The student sees only the distribution for basically the student only sees the best translation of the teacher, not the actual. It doesn't try to approximate fully the output layer distribution of the teacher. The reason why we have done this is mostly because it's much faster to train that way, and if the student wants to approximate entirely the teacher distribution, I don't think the distribution would be that peaked, which would make the use of beam search necessary, and we don't want to use beam search at translating students. We want to just use greedy decoding. But of course this is up to experiments. If I'm not aware of any papers that have contrasted the two methods specifically for the machine translation case. There might be some, but the difference in quality wouldn't be anything to marvel at. So in this case, back to our gem, we basically say quantize bits 8, and then that means that the gem implementation during training will only produce something that is similar to what would be it would produce if it was quantizing. Now we add this to our configuration and we want to put valid frequency to 200. And fine-tuning is really fast. It takes maybe a few thousand mini batches to get the optimal result. If you continue fine-tuning later on, you're gonna get significant decrease in quality, and this will help recover blue score especially with smaller student models. You can get up to 1 or 2 blue points recovered from smaller students. So everything that you can do with this, basically now you can produce translate locally. If you do a teacher model, this sort of instantaneous translation is the one Kenneth showed. Let's see, I can run my local copy of translate locally. But basically Kenneth showed it earlier in the tutorial that what you can achieve with the student models. If you don't have a student model, good luck getting that translation quality. Yeah, so and I can even copy my whole text here and paste it into translate locally, and we're gonna get translation right away. Here you have translation guide in Spanish. Okay, so let's go to caveats. Yes, as Kenneth said, it looks slightly faster when it's not limited by the zoom frame rate. So the next step is caveats. Quantization does affect different models differently, so also same is true for student models. So always test before you deploy. Try different configurations. We talked about lexical shortlisting that is known to cause quality issues with small mini batches. Current research is moving away from lexical shortlisting. We're going to talk about this slightly later. And that's it. Any questions so far before we move on to the advanced topics? I don't see any. But if you have a question, just unmute yourself or type it on the Zoom chat. I'm monitoring that. So, advanced topics. Hyperparameter tuning for speed. Mini batch 16 is not a hard and fast hyperparameter. Depending on the CPU you have, the amount of cache, the amount of RAM, maybe you want to increase the mini batch size, maybe you want to decrease it. Try it out, that depends on your hardware. Next step is efficient GPU decoding. So there are a couple of differences between CPU and GPU decoding that we need to be aware of. So first, you need for a GPU, basically translation speed scales almost indefinitely with the mini batch size. As long as you increase the mini batch size and it is a multiple of 8, the GPU will go faster. And the only limit that you have is how much memory you have. For a 3090, you have 24 gigabytes of memory. So if you do a workspace of 18 gigabytes and do a mini batch size of 768, that would be a good starting point. Shortlists don't improve translation speed on the GPU, which is great because we can just ignore that. I think Canon-based shortlist might improve translation speed on a GPU if it is implemented efficiently, but I don't think we have efficient implementation for a GPU yet. We have, in fact, experimented with 8-bit integer decoding on the GPU, but we don't get any performance gains based on compared to just using float 16. And we do get the associated quality drops that you would do when you go from FP32 to Int8. So this is also good news. It means that you can just provide the FP16 argument and forget about it. I'm not gonna demonstrate GPU decoding on my computer because once I do so, my host screen sharing session is going to hang because the GPU is going to be 100% occupied. But you can try to decode some of the test sets on GPU. The only thing that you need to do is you need to change, instead of specifying CPU threads, you need to specify something like, oh, actually I have a machine here. Okay, let's go. Let's try to do some GPU decoding. Can we do it here? So if we do marathon ens.student.tiny11, let's see, batched okay, let's see how is the server occupancy at the moment. A few people, a lot of people running. Okay. How is the GPU occupancy? Nobody is running. Okay. So if we do batch translation, CPU threads 12, yeah, that's gonna finish in a few seconds. I'm just gonna leave it here. Yeah, okay, finished. That's 14 seconds. So if we try to go on the GPU, if we say -D0, so this means we're sending it to the first GPU only, and we're already done. So we have 12 threads here, and it took 14 seconds, and we have one GPU, and we can further increase quality. So like, let's see, if I provide something like workspace 12,000, let's say workspace 18,000, and mini batch 768, FP16, and maxi batch 2000. Let's see how much time we're gonna get here, and we're down to 2.5 seconds. So we got like 100% improvement, like 50% improvement on runtime, more than 50% improvement on runtime by just specifying better flags for GPU decoding. So yeah, that's GPU decoding in a nutshell. It's you can try it out in the server or on your own GPUs. Basically, you need to tune the hyperparameters based on the GPU that you have, and it is many times faster than CPU. Like just one GPU here is much faster than 12 threads on the server. Okay, now we're gonna talk about advanced quantization options. Marian supports two types of integer backends, Facebook Gem and Int Gem, which deliver different performance depending on the model type and architecture. FBGM usually tends to deliver slightly higher translation quality because we have not fixed some issues of IntGem, but this is not always going to be the case. IntGem supports much older hardware, so you have things from SSE3 to AVX512 VNNI, whereas FBGM only supports AVX2 and AVX512 machines. FBGM doesn't support recognizing the architecture at runtime, so you need to binarize the model in advance based on the hardware you're going to run it, which is not convenient, especially if you're running on a cloud and there's different types of CPUs. Both InGem and FBGem have int16 format, which is not as fast as the int8 format, but it could potentially deliver better translation performance in some cases. So if you can't get decent translation performance with 8-bit integer, you should try using 16-bit integer. This might be useful when you want to decode fast with teacher or some other things. Just always try before you ship evaluate. So we have a much faster fork of Marian. I have linked to it on GitHub. There's instruction about how to get it. It doesn't have, so now it's like about a year behind of master in terms of features. So you get almost everything in there that you would reasonably want to use if you want to absolutely get the best speed, especially for CPU decoding. We also have a faster GPU fork. I'm going to share it later because it's not here, which is also kind of behind Marian Master. There's a couple of patches from NVIDIA that are pending before they get into Marian Master until Master can be as fast for GPU decoding as our fork. Okay, there's that, and now research direction. So I will, in this section, I'll talk briefly about what is the current research, what are the current things that are done in research that are not covered in this tutorial, but you might want to consider them when creating efficient models. So one of them is using deep encoder, shallow decoder. Basically, we have a 6-6 architecture by default. That's 6 encoder layers, 6 decoder layers. But it has been shown that you can increase the number of encoder layers and decrease the number of decoder layers and get pretty much the same translation quality, but this is much faster too. So to have a 12-1 architecture, if it has the same translation quality of as a 6-6 architecture, the 12-1 architecture will always be faster, even though technically it has slightly more parameters, because the decoder is the most expensive part of the translation, because the autoregressive part happens in the decoder, whereas the encoder, everything can be pre-computed at once and in a batch manner, whereas the expensive attention in the decoder cannot. The next thing is, if you have a lot of data, if you have like more than 50 million sentences, then transformer big might actually not be big enough for you, and you might get increased translation quality from increasing the number of parameters of your model. Now, the thing is, you can just go deeper. You can increase the number of layers, but deeper models train with more difficulty. It's a thing you spend a lot of time getting hyperparameters right for the learning rate, for the warm-up duration, and so on. And you can increase your model size by just making the model wider, increasing the FFN dimension, the head dimension, the embedding dimension. This will make your model more expressive without actually making it deeper, and will allow you to get some extra quality. And finally, as we talked, I'm rather skeptical of the current shortlists, because its inability to deal with expressions or idioms. The way to get around this and not have a massive output layer is to use KNN based shortlisting. I have linked two papers with it. In order to use it with Marian, you need to provide the option output approximate KNN, but not just any model will work with the shortlist. Your output layer cannot have a bias. So in order to use this model, you need to pass the option output omit bias during training. Um, so this is all very experimental stuff. Even though it is currently in Marian, this is mostly stuff from the non-public master, and it's considered early access feature. Don't expect to get great results or great speed out of it at the moment. Another direction that you may consider is pruning. As you know, teacher models, they take forever to train, and then translating the data that can take weeks depending on how many machines you have and how much data you have. So instead, what you can do is you can try to start training a teacher model and prune as it goes in order to reduce the number of parameters, and hopefully start training a teacher and end up with a student model directly. This would be really great if it worked, but in practice you get better. I mean, it does work, but you get better Pareto trade-off by doing proper teacher-student as opposed to relying on pruning. I have linked a couple of papers with it. And this is the end of this tutorial. I have added a section of helpful reading where I have put several papers. I have linked to the previous tutorial of the empty marathon, which was given by Roman 2 years ago. You can also refer to it. It is slightly different. It has different information. Maybe he explained some things better than me. It's worth visiting. I have kept notes. I'm going to add some extra information to the tutorial after we finish. And yeah, this is it. So please take your time, ask me any questions, go ahead, anything. Okay, I guess not right now, but yeah. Okay. Yeah, okay, well, thank you guys for your time and attention. Hopefully it's useful. Okay. Okay, thank you. I am going to stop sharing the screen right now. Many thanks to the people that came again, because speaking into the void is not nice, and it's nice to see such a full room on Zoom. Okay.